Hey, what are you doing the next 5 minutes? Nothing? Then, let's talk about deep learning. Deep learning is a specialized subset of machine learning that uses artificial neural networks inspired by the human brain to solve complex problems. Unlike traditional machine learning, which often relies on manual feature extraction, deep learning automatically learns patterns and representations from raw data, making it incredibly powerful for tasks like image recognition, natural language processing, and speech synthesis. Deep learning sits within the broader field of artificial intelligence. Think of AI as the overarching goal of creating intelligent systems, machine learning as the approach to teach systems using data, and deep learning as the cutting-edge technique that drives many of today's AI breakthroughs. It's the technology behind tools like ChatGPT, facial recognition, and self-driving cars, making it a game-changer in modern IT and software development. At the heart of deep learning are neural networks, which are inspired by the human brain. Let's break down their basic structure. A neural network consists of three main layers: the input layer, hidden layers, and the output layer. The input layer takes in raw data, like an image or a piece of text. This data is passed through one or more hidden layers, where the real learning happens, and finally, the output layer delivers a result, such as classifying an image as a cat or a dog. Inside these layers are artificial neurons, which are connected to one another. Each connection has a weight, representing its importance. When data flows through the network, each neuron performs a mathematical operation on the input it receives, multiplies it by the weight, and passes it forward. To make decisions, neurons use activation functions, mathematical formulas that determine whether a neuron should fire or stay inactive. Common activation functions include rectified linear unit for introducing nonlinearity and sigmoid for probabilities. These layers, connections, weights, and activation functions work together to help neural networks learn patterns in data, forming the foundation of deep learning. What sets deep learning apart is its depth, both literally and figuratively. First, deep neural networks have multiple hidden layers, often dozens or even hundreds. This depth allows the network to learn increasingly complex representations of data. Secondly, these layers enable hierarchical feature learning. Lower layers might identify simple patterns like edges or colors, while higher layers combine these to recognize complex concepts like faces or objects. This mimics how our brains process information, building understanding from basic to complex. Lastly, compare this to shallow networks with just one or two hidden layers. While effective for simpler tasks, they struggle with complex, high-dimensional data. Deep networks, on the other hand, can untangle intricate patterns and relationships, making them powerful tools for tackling sophisticated problems. For example, for system management, deep learning models excel at anomaly detection, identifying unusual patterns in network traffic or system logs that could indicate security threats or performance issues. In user interaction, deep learning drives natural language processing for intelligent chatbots and automated documentation systems. These applications are just the tip of the iceberg. Deep learning is continuously opening new possibilities for automation, optimization, and innovation across the IT landscape, transforming how we develop, maintain, and interact with software systems. Now, let's explore three specialized architectures deep learning relies on to tackle diverse tasks. First, convolutional neural networks are designed for grid-like data and image processing. They excel at detecting patterns like edges, textures, and shapes by using layers that apply filters to input images. How? By using convolution, which is a reduction of the number of weights that the model needs to learn by summarizing the image into fewer pixels. CNNs are widely used in applications like facial recognition, medical imaging, and self-driving cars due to their ability to classify and analyze visual data efficiently. Next, recurrent neural networks are tailored for sequential data, such as text or time series analysis. Unlike traditional networks, RNNs have a memory mechanism that retains information from previous inputs, allowing them to understand context and temporal dependencies. This makes them ideal for tasks like language translation, speech recognition, and financial forecasting. However, they do have limitations, such as long-range dependencies, data processing parallelization, and computational efficiency. Thus, let's talk about our third architecture. Transformers revolutionized natural language processing by addressing the limitations of RNNs. They process entire sequences simultaneously using self-attention mechanisms, enabling models like GPT to generate text, summarize content, and power chatbots with remarkable accuracy. These three architectures showcase the versatility of deep learning across domains, from vision to language and beyond. Let's now move on and discuss how to best train these deep neural networks. Training deep neural networks is a complex process that relies on three key elements. First, backpropagation and gradient descent. These algorithms work together to adjust the network's weights. Backpropagation calculates the error gradient for each neuron, while gradient descent uses this information to update weights, minimizing prediction errors over time. Second, large datasets are crucial. Deep learning thrives on data. The more, the better. Large, diverse datasets help models learn robust features and generalize well to new, unseen data. This is why companies like Google and Facebook, with access to vast amounts of user data, have been at the forefront of deep learning advancements. Lastly, GPU acceleration is vital. Training deep networks is computationally intensive. GPUs, with their parallel processing capabilities, can perform these calculations much faster than CPUs. This has dramatically reduced training times from weeks to hours, making deep learning more accessible and practical for real-world applications. Understanding these elements is key to implementing effective deep learning solutions in IT environments. While deep learning is incredibly powerful, it comes with its challenges. First, computational requirements can be significant. As we just mentioned it, training deep neural networks requires high-performance GPUs or cloud resources, which can be costly and time-intensive. Second, there's the issue of interpretability. Deep learning models are often considered black boxes, making it difficult to understand how they arrive at their decisions, which can be a concern in critical applications. Lastly, bias in training data is a major consideration. If the data used to train the model is biased or unrepresentative, the model's predictions can perpetuate or even amplify those biases. Thus, the importance of building responsible AI models. Addressing these challenges is key to responsibly and effectively using deep learning in real-world IT applications. To conclude this high-level tutorial, let me say that deep learning has revolutionized AI with its ability to process vast amounts of data and uncover complex patterns, powering applications from image recognition to natural language processing. Its potential to transform IT workflows, like automating tasks, detecting anomalies, and enhancing user experiences, is immense. As IT professionals, now is the time to explore deep learning. Don't hesitate to experiment with frameworks like TensorFlow or PyTorch, and think about how it can solve challenges in your projects. And, obviously, reach out if you need guidance in how to best jumpstart your journey into AI. And that concludes our journey into the fascinating world of deep learning. Looking ahead, our next tutorial will explore AI agents, intelligent systems that bridge the gap between virtual intelligence and real-world applications. These agents represent the cutting edge of AI, where software doesn't just compute, but actively interacts with and adapts to our environment. If you're eager to understand how AI is reshaping technology, hit that subscribe button and turn on notifications. You won't want to miss our deep dive into AI agents, where we'll see how virtual intelligence tackles real-world problems. Thanks for watching, and I'll see you in the next tutorial.